In this video, we'll review some fundamental elements of a probability model. In particular, we'll explore the elements of a probability model for a discrete random variable x in a marginal setting, that is, when modeling the behavior of x alone. That said, these same ideas can be tweaked and extended to continuous random variables, to joint models, that is, modeling the behavior of x with another variable y, and to conditional models, that is, modeling the behavior of x given data on another variable y. Consider an example. Let x be the rating that a customer gives to a certain restaurant. These ratings can range anywhere from 1 star to 5 stars and can vary from customer to customer. The randomness of the ratings from customer to customer can be modeled by the following probability mass function, or PMF, f of x. For integers x from 1 to 5, f of x equals 1/55 times x squared. Plugging in each possible outcome of x, we can also reframe the PMF in the form of a table. And we can turn this table into a plot of the PMF. Let's pause to consider some details. First, the PMF in all its forms, formula, table, plot, illustrate that the plausibility of a customer's rating x steadily increases as x increases. For example, there's a 25 out of 55, or roughly a 45% chance, that a customer gives the restaurant 5 stars, and only a 1 out of 55, or roughly a 2% chance, that they give it only 1 star. Second, notice that the probabilities of all possible outcomes sum to 1. That is, our model accurately accounts for all possible outcomes of restaurant ratings x. This same idea is written here in summation notation. Next, let's dig into the elements of the formula itself. First, and importantly, the support of a PMF indicates the values of x for which the model is defined. That is, it indicates the possible outcomes of x. Here, our PMF indicates that a customer's restaurant rating can range from 1 to 5 stars. Unfortunately, people often forget to include the support when writing out a PMF. Don't do this. Knowing the possible outcomes of x is fundamental to understanding its behavior. Thus, without the support, a PMF is meaningless. Moving on, the kernel of a PMF captures all information about our variable x. It includes the support, hence the possible outcomes of x, along with the relative plausibility of these outcomes. The kernel here indicates that a restaurant rating x can range from 1 to 5 stars, where the relative plausibility of a given rating increases with the rate of x squared. For example, plugging in the possibilities of an x equals 5-star rating and an x equals 1-star rating, we get x squared outcomes of 25 versus 1. Thus, a 5-star rating is 25 times more likely than a 1-star rating. Finally, there's one last piece of a PMF to consider. The normalizing constant, here 1/55, is simply a constant, a fixed number that ensures our PMF sums to 1. That is, the normalizing constant ensures that the PMF is appropriately scaled. Now, though our constant of 1/55 here is pretty basic, normalizing constants can actually get really messy and sometimes even really tough to calculate. Luckily, it doesn't hold any important information about x that isn't already accounted for by the kernel. Thus, we can define the PMF of x without the exact value of the normalizing constant. Mainly, recognizing 1/55 as just some constant c will often drop the constant from our formula. That is, we'll simply note here that the PMF f of x is proportional to x squared. To better understand the idea of proportionality in general, not just probability models, consider some examples. First, suppose we want to model a person's height. Let x be the height in inches and y be the height in centimeters. So x and y are both measuring height, just on different scales. Specifically, height in inches equals 2.54 times height in centimeters. That is, x equals some constant c times y. Thus, x is proportional to y. Second, suppose we're measuring the current outdoor temperature in degrees Fahrenheit x and degrees Celsius y. Again, x and y are measuring the same things here, just on different scales. However, the conversion is more complicated. X equals 9/5 times y plus 32. Because we have to tack on this constant of 32, we can't simply write x as some constant c times y. That is, x is not proportional to y in this case. So let's consider the impact of the normalizing constant on our model of restaurant ratings x. Here we have our original normalized PMF of x. Normalized meaning it still includes the normalizing constant of 1/55. Thus, it sums to 1. Dropping this constant produces an unnormalized PMF. F of x is proportional to x squared. As expected, this unnormalized PMF does not sum to 1. However, notice that the table of the unnormalized PMF appears similar to that of the normalized PMF, just on a different scale. This is perhaps easier to observe when plotting the PMFs. The only difference between the two plots here is their y-axes. They're on different scales but preserve the same proportionality. Mainly, the unnormalized PMF preserves all of the important information from the normalized PMF. It preserves the possible outcomes of x and the relative plausibilities. For example, the relative plausibility of a 5-star versus a 4-star review is the same in both the normalized and unnormalized versions of the PMFs. In general, a normalizing constant just ensures that a PMF is appropriately scaled. It doesn't tell us anything about the possible outcomes of x or their relative plausibility. All of that important information is defined by the kernel of a PMF. That is, if we know the kernel, we know the PMF, or a PMF is defined by its kernel. To convince ourselves of this, let's consider one last example. This time, let's start with an unnormalized PMF. Here, f of x is proportional to 15 minus x, where x can take on values of 5, 7, and 13. This unnormalized PMF is re-expressed in the table here, and it doesn't sum to 1. Yet, though it's unnormalized, the proportionality notation indicates that this function preserves the relative plausibility of the outcomes of 5, 7, and 13. For example, comparing 8 to 2, an outcome of x equals 7 is 4 times more likely than an outcome of x equals 13. Though this unnormalized PMF tells us everything we need to know about the relative plausibility of x outcomes, we can also normalize it if we want more specific information. For example, exact probability calculations. To this end, we can divide our unnormalized formula by its sum of 20. To convince ourselves that 1 out of 20 is indeed a valid normalizing constant, check out the resulting PMF table. Indeed, the normalized probabilities sum to 1, while also preserving the relative plausibility of x being 5, 7, or 13.